describe that. That's the Institute of Europe, and actually quite definitely so. I mean, I think that that was also set up by Oppenheimer in part, right? I mean, with the idea of having an institute in Europe. Thibault is well known for his work on gravitational radiation and has probably begun before many and obtained many results that even impinge on the mathematical structure of general relativity, on the completion, the conformal compactification of spaces, but also he has done work that is, and would be relevant for gravitational wave detection and the determination of waveforms, which I think would be
yes.
what is being
talked about. So, and please don't hesitate to ask questions. Everybody should, if you get lost, you have to ask. So, one of the main, first let me, just for you, mention that for the 10 years of the first detection of gravitational waves, last January in 2025, a very interesting system has been discovered, which has it's a coalescence of two black holes with the same masses essentially as the first source, 30, 26, something like this, but the signal to noise ratio is 80. It's the largest signal-to-noise ratio ever for LIGO among the 300 sources. And because of this, one could do exquisite comparison to general relativity. And in particular, the point is here that one could check that the frequency and damping time of here, the first quasi-normal mode, after the two black holes merge, and then the remnant, which is vibrating with QNM, agree. These are fractional deviations compared to the curve predicted values, and you see like this one is at the 2% level. Okay, it's the first time that we have a 2% confirmation that curve black holes describe nature. Okay, are there? And why I'm saying this is because to get this level, you need to have an analytical description of the full waveform from -infinity. During the
this thing is normalized to 1 or something,
yes,
right?
It's
so
fractional.
It is 50 per, okay.
Fractional. That's why
so it's a very good accuracy.
There is a hat on it. Yes, it's a very good accuracy. This particular result was obtained by using the effective one-body waveform, which will be one of the focus of this talk, because the effective one-body approach to the binary system had been invented 25 years ago to make the first prediction of what is the full waveform emitted by two black holes going around and then merging and then vibrating.
Sorry, Thibault, and since this is like 2%, it means they have measured like the entire spectrum of quasi-normal modes, like other frequencies.
Yes, others. They have this one, the next one, and even a third one. Okay.
So like it's
the beginning of black hole spectroscopy for the first time. Right. There have been claims that with the first observed thing, one could see this, but there were people saying no. Okay. Here, the amount of, the fact that there is a signal-to-noise ratio of 80 in the full signal is like 2/3 of this signal-to-noise ratio is in the in-spiral and merger, and let's say 1/3 in the post-merger. Okay, that's why you have a lot of signal for the first time. Before it was very fuzzy. Okay. Anyway, the effective one-body is an analytical method which has been recently in synergies with many things. Traditionally, it was in synergy with post-Newtonian approaches. More recently, and that will be the theme, with post-Minkowskian, that I will describe, and with string theory and quantum field theory. I will describe the quantum amplitude version, numerical relativity, and tutti frutti. Okay, I will define these terms during the thing. So what is the effective one-body method is a method which during the in-spiral replaces the complicated two-body Hamiltonian, let us say, or the computation of the diagrams of the interaction of two bodies by an effective particle moving in some effective metric. It's a generalization of Newton's famous thing that the two-body problem is actually equivalent to one body of mass mu, the effective mass, moving in the same potential as the two-body thing. But here you need to do that in full GR, so it's technically more subtle, but I will describe what is needed. Then the effective one-body method was able to push the analytical description up to the merger, and then this was something published in 2000 which predicted the full waveform for the first time. At the time there existed no numerical relativity. It took 5 years before numerical relativity could exist, 7 years for numerical relativity to be comparable in accuracy to this thing. Now, yes, so if, yes, oops, no, this should work here, yes. Just to have you an intuitive meaning, so the effective one body is describes the motion or the relative motion between the two bodies by an Hamiltonian that I will quickly describe, and with a radiation reaction force, which means the two bodies, it's a non-conservative dynamics. There is a conservative part, and radiation reaction means you lose angular momentum energy, so you get closer and closer. And when you get at a certain point, when they are very close, the formalism predicts itself when it stops, and what is the sum of quasi-normal modes, the ring down signal that you had, and it is based on many resummation methods. Okay, you don't use perturbative theory directly. You have the information from perturbative theory, and then you massage it in the best possible way to resum, in particular, the waveform, and I will describe this soon.
And what do you get, like 10%?
Exactly. The first thing, I will not describe it, when there was the first comparison, it was 90% accurate. Okay, there was a 10% difference. And as I will describe now, in order to get not a 90% agreement, but a 99.999% agreement, you use more numerical relativity information. And I will describe why in an analytical framework you can put information from numerical relativity, and then it's an efficient way. Just for information, to compute one numerical relativity waveform still takes 1 month for one value of the two masses and the spins. Why it takes, it can take milliseconds if you have an analytical description of this type. So you need an analytical description, but you also need, for accuracy, numerical relativity complete way. Okay.
Can I ask you, have people tried machine learning?
And now, yes. Evidently, many people are talking about machine learning now. It's still, okay, let's not discuss it. And people know that one has to improve. It's not clear when, maybe in the future, the analytical thing will be useless and everything will be done with machine learning and numerical relativity. It's not yet the case. Okay. Now, traditionally, the way one was using perturbative calculations to define the UB was based on post-Newtonian theory, which means expansion in small velocities and small also binding energy. And the basic idea was to identify gauge invariant quantities, because when you do a post-Newtonian computation, you have equations of motion, Hamiltonians that have hundreds of terms, and 90% of these coefficients are gauge-dependent things, okay? There is a very small part of it which is gauge invariant, and one way to get it is to think what we call in France the Delaunay Hamiltonian, which means the energy as function of the action variables, the radial action and the action over the two angles. This is a totally gauge invariant way, and if you think a little bit quantum mechanically, this is essentially the classical limit of the spectrum, okay, of the quantized spectrum, because in Bohr-Sommerfeld, the action variables are quantized in n+1/2 h bar, okay? So anyway, this was the way it was initially conceived to extract gauge invariant information from perturbative calculations. Recently, and this will be the emphasis of the new thing, One is using now a new way of getting information about the gravitational interaction of two bodies, which is to do scattering, both quantum scattering, quantum amplitudes, and their classical limit, which means essentially the scattering angle. When you shoot two black holes at a certain distance, they interact, they attract, and then there is a scattering angle. And there is a very simple dictionary in the sense that if you know the scattering angle as function of incoming energy and the impact parameter, or total angular momentum, then, for instance, and you expand it in inverse impact parameter or inverse angular momentum. So this term is the lowest order, one graviton exchange, first order in G. So it's called now, I had introduced this 40 years ago, post-Minkowskian. This is first order in G, second order in G, third order in Newton's constant. And each coefficient here gives the basic element of the effective one-body description, which is to say that this effective particle of mass mu lives in an effective metric and satisfies a relativistic mass shell condition, p squared plus something equal to
Sorry, what is G again? Velocity over c or something?
G, which variable here?
You expand scattering angle.
J.
Yes, J.
Sorry, J.
Sorry.
Right.
I've just been in a
Scattering gamma is Lorentz factor or not?
Yes, gamma is the Lorentz factor between the two word lines.
And
Okay.
J is what? Impact parameter or something?
So J is the total angular momentum, and G, because I still G, is Newton's constant.
Right, G of
And
course.
then
Sorry,
this is
J,
dimensionless.
right.
This is dimensionless. G M1 M2 over J is a dimensionless number, which is essentially linked to the inverse impact parameter. So it means they fly at a certain distance, and you expand the scattering angle in inverse of the impact parameter.
So it is an impact parameter only normalized to something. J.
Yes.
Yeah, J is P times B, essentially. It's the impact parameter times the momentum in the center of mass, right? Now, the important point is that the knowledge at each order in this inverse impact parameter immediately, for instance, this thing is equivalent to saying that you must take an effective metric which starts with Schwarzschild metric, okay? And then the second term gives an extra term in 1 over r squared that you need to add to this mass shell condition. So there is a very simple dictionary which is written here. This term, Q2, is Chi2, the second term. This term is Chi3, essentially. So very simple gauge invariant. From if you have a post-Minkowskian computation of the scattering angle, you can write immediately an effective one-body mass shell condition, which is equivalent to an Hamiltonian for the conservative dynamics. So it's a different way of doing the things which was done before.
Just to understand, you said there's a connection between like the free problem and this Hamiltonian, which will describe the bound system.
Yeah, essentially, okay, scattering
Same,
is an attractive force, so the
Right.
scattering angle is a function of the force between the
Right.
two, and from the force you have the Hamiltonian for the bound case. So,
Yeah.
and then you can describe the bound case starting from the scattering case. The point about numerical relativity, let me just make it, when you have this effective metric, which represents in a simplified way the interaction between two black holes, and among the components of the effective metric, the most important one is G00, which in the Schwarzschild case, you know, is 1 minus 2 gm over r. And we recognize in 1 minus 2 gm over r the gravitational potential, essentially, gm over r, attractive. When you are in this setting with two masses, not in the probe limit of one test particle in a Schwarzschild black hole background, but two comparable mass black holes, you have a G00, which when you compute it perturbatively, is denoting gm over c squared r as u, is 1 minus 2u, this is Schwarzschild, and all the rest, they have a factor nu, or nu square, where nu is the symmetric mass ratio, m1, m2 divided by the sum of the mass square. So nu is 0 in the probe limit, and 1/4 in the comparable mass case, and this is a way of continuously connecting the equal mass black hole interaction to the probe limit that we know well. Here for non-spinning case, evidently, this is generalized for spinning case when I have two spins, you need to base the Kerr matrix on that.
But this approach is different from post-Newtonian, right? That's the
Yes.
whole point.
That's the whole point, yeah. Post-Newtonian, yeah, I did not spend time here, gives, long formulas which get useless and a lot of gauge-dependent information. Here, each coefficient here comes from a PN calculation, from a post-Newtonian, okay? This
Then why
will-
do you need scattering to put...
I will explain why.
Oh, okay.
Okay, but the point I want to make here is, for instance, here, this is at the fourth post-Newtonian level. This is the third post-Newtonian, this is the fourth post-Newtonian, this is the fifth post-Newtonian level. And what you do is, this has not been computed yet, this coefficient, which should exist analytically. So what you do is you say, let's put a coefficient that I don't know, and we tune we make a comparison to numerical relativity, and then you find that this value of A6 with this number, deduced from numerical relativity, makes a very good description down to merger. Just to explain how one can combine in an analytical base numerical relativity information with a purely analytical thing.
And sorry, this is to be used only during the in-spiral phase? Or?
As we have seen in the small simulation before, yeah, you use this effective one body up to the moment where they merge, essentially, and the moment of merger is defined within the formalism, and when they merge, you attach a ring-down signal made of a sum of quasi-normal modes.
And how is it defined? What happens to you at the moment of merger?
So, in the formalism, there is a way of selecting U is of order 1, okay, at merger, but it is decided by the formalism, okay. There is the orbital frequency, which is defined here, reaches a maximum, and this is considered, I mean, it's part of the formalism at the moment where you cross the effective light ring, okay? Linked to all work by Ruffini, Thibault, and Davis. I don't want to enter the debate because I want to talk about the recent things.
Excuse me.
Yes?
If we go to the previous slide, could you repeat the same then with these nice results by Zwiebel and Paul using QFT techniques instead of using the numerical relativity?
This is the point now that I'm reaching, okay. But another point I want to make, it is very important to use, okay, so we don't use post-Newtonian in non-resum form, okay, it is messaged this way, and we don't use also post-Newtonian computation of the waveform. The waveform is resummed in the best possible way you can think of by factoring an infinite number of logarithms, okay, all the leading logarithms. This had been defined long ago, and I'm saying this because recently, with the activity in EFT and also in quantum Seiberg-Witten connection with this, okay, with the confluent Earn equation, there is a work by Fucito, Morales, Cipriani, which is now being used to improve this resummation, okay. But this resummation works very well, and maybe it can be further improved, so that the same analytical information can be even better, and you need less things linked to numerical relativity. Now, just this slide is just saying, up to now, I had 2 non-spinning black holes, but evidently we want to have arbitrarily spinning black holes. And this introduces complication, but essentially there are several versions of UB with spins, okay? And it's very important to include spins. Now, coming to Zwiebel, the reason why Zwiebel did this is because in 2016 and 2017, I met him, and I wrote this paper which was combining 2 things. First, the work of Amati, Ciafaloni, Veneziano, which was the only 2-loop computation of the scattering, computed in string theory and at ultra-high energy. And there did not exist any classical computation of the scattering at 2 loops. So I had urged, it's written somewhere here, amplitude experts to use their methods to compute what did not exist, which was post-Minkowskian expanded, which just means any arbitrary velocities without making a small velocity expansion at the 2-loop level, which means GQ. Okay, 2-loop level means you compute the interaction of 2 word lines, massive word lines, at this level, okay? And several months later, Chung, Rostin, and Solon also talked about that and introduced a dictionary between quantum amplitudes, because now, yes, so I won't discuss here the subtleties of Zwibern did all this computation with a quantum scattering amplitude, and then from the quantum scattering amplitude, actually you need to subtract all quantum effects to have the classical scattering angle. Okay, then I will continue about this. Okay, and at the beginning it was a very efficient way, using the double copy and everything. Okay, now it seems that because they are super classical terms, it's not so efficient to start with a quantum amplitude, because you have many hyperclassical things.
Why do people compute scattering in quantum?
The main reason was that Zvi is an expert in this, in quantum amplitudes, and he had all the tools, and in 3 months he could do the computation and got it first. And he knew how to extract from the quantum amplitude the classical one. There are several
But what do people who compute quantum amplitudes do? What do they want to achieve? I'm just curious. I mean, what is the meaning of this quantum computation?
Okay, first, as you know, Zwibern had spent years trying to prove that supergravity was finite, but this is a 7 loop. I mean, you think the first counter term is at 7 loops. And at 5 loops, he found interesting things, and then, okay.
So this is done, in fact, in supergravity?
Yes.
Ah,
no,
okay.
This computer is done in gravity, okay.
This is done in normal gravity?
It's normal gravity, although the supergravity computations are also done, they are simpler, okay? Once you have the good formalism, okay? But then you take away b mu nu and the dilaton, okay?
But sorry,
there are many ways to take it away.
Can you explain, sorry, for a humble astrophysicist, there is quantum gravity is divergent or whatever, but if you do a computation at 2 loops with normal Einstein-Hilbert action, you still get something meaningful.
Yes, the UV divergences are never a problem there. Okay, they are linked to what happens when you have gravitons connecting to the same world line. And the divergences of quantum gravity are not
in this 2-loop computation.
They are there, but you can eliminate them immediately and keep the long-range interactions.
Okay.
Because we are interested in what happens in the field between, you know, you are not interested, and you can separate them. They are not a problem, technically, even at 4 loops, which is the level now. But what I want to describe is, so here I was saying, yes. So given, and I will re-describe this, given a scattering angle computed to all orders in V over C, but as an expansion in G, there are several ways of converting this in an effective one-body Hamiltonian that can be used to describe the merger of 2 black holes. And the reason why I'm saying this is that you have choices, and essentially, and in a sense, nicely, one way is to replace the scattering angle by a potential W, which is coefficient over 1 over R, which is essentially the relativistic 1 over R potential, then 1 over R squared, then 1 over R cubed, and 1 over R4. And the simplest thing, which is, you know, textbook Newtonian mechanics physics, that P square is equal to the energy plus the potential, or minus the potential, okay, gives a fully relativistic description of the relativistic scattering of 2 black holes, okay? So, and then you can convert this in an explicit Hamiltonian, but then there are several choices that I will describe in the next slide. I'm saying this because recently, okay, so traditionally the effective one-body used post-Newtonian information and had an explicit Hamiltonian, okay? Why? When you start from post-Minkowskian gravity, if you want, okay, as appeared very quickly on the previous things, yes, here, this potential, yes, when you convert post-Minkowskian gravity in a potential W, this potential is energy dependent. It depends on the Lorentz factor between the two world lines, which means that this condition is not an Hamiltonian, because it's P square equal energy, this is energy, P infinity square is gamma square minus 1, so it is the energy. But energy appears also in these coefficients. So if you want an Hamiltonian, you have to solve this equation for gamma in terms of P square. But these coefficients, that I will not show, they become very complicated, okay? At 2 loops, okay, you have some logarithm and arctangent. At 3 loops, you have square of complete elliptic integral. And at 4 loops, as I will say, you have periods of Calabi-Yau threefolds, okay? Objects that are functions of gamma, but they are terribly transcendental functions of gamma. So actually, you cannot solve explicitly this. So what had been done at the beginning, I had suggested that, and my former PhD, Alessandra Bonanno, did it in some cases, is to solve perturbatively gamma in terms of, because you can solve this, gives a simple function here, and this you can put as perturbative things. But then it makes big differences when you use it to compute waveform. And recently, just to say that something exists, recently we introduced a new approach to using post-Minkowskian gravity to define waveform, which we call the Lagrange EOB waveform. Lagrange, because we put a Lagrange multiplier. You have a mass shell condition, which is a very complicated function of the energy. And you don't solve it for the energy as function of P square. What you do is you put it as a constraint with a Lagrange multiplier in an action. And then, numerically, you can integrate the equations of motion this way without ever solving explicitly the constraint, but it is constraint. You solve it at the initial point, and then it is satisfied. And then it gives, so unfaithfulness means that you compute a waveform analytically, and then you do its scalar product, inverse weighted by the noise of LIGO, against the best numerical relativity waveform that exists. And then this thing should be equal to 1 in the perfect world, or at least 0.9999. Unfaithfulness means 1 minus the overlap, which means that unfaithfulness of 510 minus 4 means you have waveforms which are quite good, okay? Which are at 99.99% accurate. Okay, just to say that this is in development, but I don't want to describe this. The only point I want to mention here is that, for instance, this is what is used by the competitor group, let us say, Alessandra. And using the same post-Minkowskian information, what is important is just the conceptual point. Using the same scattering amplitudes and scattering angles, depending, you put it in the formalism in this way or this way, and then you get effective potentials which in LEOB are very similar to what is first in Newtonian mechanics and in Schwarzschild spacetime, what would be an effective potential. This is the centrifugal barrier, and when you lose angular momentum, the centrifugal barrier decreases, and then you reach a point where the two objects are so close that they plunge towards each other because this barrier disappears. Why, and this is fully post-Minkowskian here. Why, in this case, you have the same post-Minkowskian information, but you solve it perturbatively, and then you get things which is very different, and which would make strange predictions. Anyway.
Particularly if you had a minimum in that effective potential, you'd have
exactly.
a stable
So
orbit. Right?
the fact that, for instance, here it would mean that you don't have a last stable orbit.
Yeah.
The two objects would always be able to, which is not very good for this. So in that case, you are obliged to stop to do something else. But just saying, depending on the same information, you can now use it in this better way. I mean, better. We think it's better. And then it looks what you want. Okay.
But this minimum would go away if they went to higher orders or something in this iterative expansion?
No, now I talk about higher order. We don't know yet. Okay, now very quickly, because I want to talk about recent things. I'm still here repeating things that I've said in 2023 in the same room, okay? And I want to go to the new things. Okay, so the first calculation at 2 loops in the sense of diagrams, third order in Newton's constant, which is called 3 pm, third post-Minkowskian, was done by, oops, what happened? Nothing. Yes, was done by the group of Weber and then reproduced by other groups. But the point is, this was motivated by the work of Amati, Ciafaloni, Veneziano, who had computed the scattering angle. Then Zwieber and his group compute the scattering angle for arbitrary energy, arbitrary Lorentz factor. But if you took the limit of ultra energy gamma going to infinity of Zwieber, one was not getting the result of ACV. And Zvi said, no problem, but actually it was a problem, but only Gabriele and myself said, it's a problem, we need to solve the thing. Why your result does not agree with Amati, Ciafaloni, Veneziano? And it took some time, a few months, and it was necessary to include radiative effects. That is to say, the loss of angular momentum, actually, as I will describe, the fact that during the collision, or during the scattering, you lose angular momentum at infinity, contributes an additional term in the scattering angle that you need to take into account. And when you do it, you agree with ACV in the high energy limit. Okay. Now, the next thing had been done at the 4th order, 4 p.m. order, first by Zwieber, including with Julio Parra-Martinez, Zhang, others, and by the group of Porto, Rafael Porto, and then also by Damour and company, including radiation reaction. So this is fully known, but there is a subtlety at this level, which is in most of the approaches to the binary system analytically, as I have described, you want to have a description of the conservative dynamics in absence of radiation reaction, and then you add radiation reaction that you compute by the loss of energy and angular momentum at infinity. But, and usually you say radiation reaction is well defined, this is the time odd, the time non-reversal invariant contribution to the dynamics, and the conservative is the time even part of the dynamics. The problem is that at this order, because radiation reactions start at order G square, you have square of radiation reaction effects, and the square of something time odd is time even, and therefore you start mixing what is conservative and what is radiative. Okay? And there is no way out. You need to take this into account, which is a subtlety. And this subtlety becomes even more subtle at the next order. Yes, so before going to the next order, let me, for the benefit of Massimo, because it's a bit technical now, so I said that in order to reconcile the result of Zwieber and the result of ACV, one had to compute the loss of angular momentum in the form of gravitational waves at infinity. Okay. And I was the first one to do this computation using the standard DeWitt-Thorne formula for radiated angular momentum, and using a non-zero shear at minus infinity linked to the incoming velocities of the two bodies. But some people complain that, like there is a paper by Veneziano and Vinkovsky saying that Damour uses the wrong definition of angular momentum but gets the right result. Okay? I told them maybe I was using the correct definition if I get the correct result. Because there are subtleties linked to BMS, Bondi, Metzner, Sachs group, subtleties linked to zero frequency gravitons. Okay. So now a new important thing is they are part of the gravitational field, which are in a sense radiative, but zero frequency gravitons. Okay. And they emit, they lose angular momentum, but do not lose energy. And it will come again in the future. So recently,
Sorry, this is still a classical effect, or
the paradox is at the quantum
okay.
because for Gabriele, saying if you start losing gravitons and energy at g cube, at g square you should not lose gravitons, and therefore you should lose nothing, no angular momentum. While classically, you compute there is a loss of angular momentum, but no loss of energy at order g square. So indeed, okay, there is a subtlety. To clarify further this subtlety, with Donato Bini, we did a fully mechanical computation, which is given two world lines, and given the subtle, because I think the thing of Carlo Heisenberg and Rodolfo Russo is linked to not taking into account fully the Fokker interaction value of P mu and G mu. When you have two world lines interacting by time symmetric exchange of gravitons, you need to modify the definition of what is the conserved linear momentum and the conserved angular momentum by adding field terms, okay? But conservative type field terms. And when doing this computation, and these terms are delicate in the sense that depending, here they are manifestly Lorentz in the Poincaré invariant defined, and then they are uniquely defined. But if you work in the St. Thomas frame, maybe you don't do the good thing, and you can get Scoot terms which modify this. So there are subtleties here, but at the end, doing a purely mechanical computation of the loss of angular momentum of the system in a Poincaré invariant way, we got the same result that I had obtained by a flux computation, okay? Which in my opinion justifies both computation, although mathematicians say that if you confirm something you assume, you are in a bad situation, but maybe both can still be wrong, okay? Anyway, the recent work of the group of Jan Plewka is the only one which has now succeeded in reaching the next level, for loop. And they did it by using, not using quantum amplitudes, but using iteration of Einstein's equations, classical scattering, but computing, evidently, using the best technology from Feynman diagrams it leads to integrals, okay, very complicated integrals. And then, first you need, and this is what is, you have millions of Feynman integrals, classical Feynman integrals, okay, these are with retarded propagators, they are not quantum Feynman integrals, but they are integrals. Then you use integration by parts to reduce them to a basis. Integration by parts took 300,000 core hours of computing time. This gets a lot now, you see.
So
Yes,
you just said that numerical relativity was
Numerical relativity uses tens of millions of core hours.
tens of millions of
Okay.
hours.
For
So
neutrons,
still-
actually for black holes, the codes are very efficient and they are of the order of millions of core hours.
Okay, so we're getting close to the
Exactly.
order of,
So now analytical thing from this thing is getting
analytical
exactly,
as a big
which
quotation
gets
mark.
heavy, and it's probably the end that people can do now. Okay, which is an interesting thing.
In these calculations, at the end of these 300,000 core hours, do you get an analytic formula that depends on three parameters or just a number? Because
No,
numerical
you get
relativity-
functions,
Yeah, but
but the subtlety. So the method to compute these integrals is a generalization. You may know the Legendre equations. When you have a Legendre complete elliptic integrals, E and K, they satisfy differential equations. Okay, dE by dk is equal to f, the other is equal to k, and things like that. So this is a generalization. You have hundreds of basis master integrals, and you want to write a differential system. And what happened at this order is they found that there was a hidden Calabi-Yau threefold. And by the way, Calabi-Yau threefold that they had to ask the expert in string theory of this particular Calabi-Yau threefold, Albrecht Klemm, who knew this thing, which is a very beautiful mathematical object. So it's fantastic to see the beauty of algebraic geometry coming for the practical question of it. What you see of this is the Picard-Fuchs equation. Picard-Fuchs is just a way of saying there is something geometrical, which is this very simple equation. So there are four solutions of this, And from these 4 solutions, you can construct the periods of the Calabi-Yau, and then you have iterated integrals. But at the end, it means you cannot write the answer in analytical form. You can compute it if you want, but it's a function of gamma defined by something. Okay. Anyway, separately from this, because now the end of the talk is to say, this is the beautiful work from the post-Minkowskian forms. But we did not stay idle in the meantime, because we had invented methods years ago which were combining the best thing we knew from post-Newtonian and self-force. Actually, this is the tutti-frutti method. So let me explain what were the ingredients of the tutti-frutti methods. The basic ingredient is an absolutely trivial fact, but which is extremely useful. I'm always surprised that saying something so trivial can prove things. It is to say that the change, the transfer of momentum during the scattering must be a polynomial in the 2 masses when you compute it in terms of the incoming impact parameter. Okay. You just solve by iteration Einstein equations, and then, okay, when you do that, you will be polynomial in G and polynomial in M1 and M2. This fact gives that the scattering angle is a polynomial of a small order in terms of the symmetric mass ratio, and this fact allows you to compute things without doing any computation. For instance, from this, the 2 PM computation, which is not at all easy, is trivial. You have nothing to do. You take Schwarzschild, and then you get the 2 PM without doing anything. You know? So it gives useful information. Now, the tutti-frutti method combines many things, including polynomiality, Delaunay averaging, self-force. Okay, you combine things, and then you are able to compute subtle terms in the interaction of 2 bodies that include non-local in time effects. Because starting at order G4, you have terms, tails. Okay, tails means the system, the 2 black holes, is emitting gravitational waves at infinity, and that these waves are scattered by the Coulomb field Gm/R of the system itself. And then these waves can backscatter on the system, and therefore you have an interaction between the 2 bodies here and the bodies millions of years in the past. Okay? It's an integral over the full time line. Okay? So by using a certain, we could go to higher than all the existing post-Minkowskian computation, but only to a limited number of V/C. So it's a complementary computation. You have a question?
Thanks. Yeah. So it sounds very nonlinear. How come we have polynomials then?
Polynomial in U for the scattering
Yes.
angle. A polynomial is already nonlinear. So what I was saying is it's by perturbation theory. At each order in Newton's constant, you must be polynomial in the masses and therefore polynomial in U. Okay, you are very nonlinear in velocities and positions. Okay, there are transcendental things happening here. Okay, but not at the level of the masses, and it's a very useful information. For instance, we could compute things which are at the 6th post-Newtonian level and which go to the 7th post-Minkowskian level, okay? So we could compute the full Hamiltonian up to 7 PM, but Pn expanded at 6 Pn, modulo only at 5 Pn, modulo 2 unknown numbers, okay? So you compute hundreds of terms, but there are 2 numbers that you cannot compute. And ideally, you want to get them either from numerical relativity or from post-Minkowskian gravity when they exist, okay? At this level. Yes, and I just want to give you a flavor. The flavor is recently we did a comparison between the predictions from this formalism and the latest results of Plewka, the group of Plewka, at 4 loops, okay? Although Plewka did not compute the full 4-loop things, but only the terms linear in the symmetric mass ratio, we could compare. Okay. We could also compare at the previous level G4 And let me just say one thing here is, because I did not say it, why the loss of angular momentum is contributing to scattering. We, long ago, 15 years ago, I think, with Donato Bini, we have proven a general formula which says that if a system loses energy in angular momentum, there will be a corresponding contribution to the scattering angle that you must add, linked to the losses, which is a very simple expression in terms of the energy loss and angular momentum loss. And I'm saying this because the group of Rafael Porto has computed the full radiation reacted momentum transfer at G4, okay, at 3 loops. And using our formula, we could extract from this the 3 p.m. angular momentum loss. J3 is the loss of angular momentum, not at G square, but at the next order, which has been computed only by, I forgot their name, yes, you see, anyway. This was a difficult computation.
You mean the group of Manohar and...
Yes, Manohar, yes, exactly, and then, anyway. So it was a hard calculation, and what is beautiful is from scattering, you can recover this and prove it is hidden in the formulas there, just to all those things exist. And also, recently, what we have shown is that there are terms now which are not only tail effects, but tail of tail. Tail of tail means you have a graviton which is emitted by the system. It interacts with the tail Coulomb GM over R once, and it interacts a second time, so it's iterated tail, and then it goes back on the system. And this is linked to the renormalization group, which appears because of infrared divergences in this computation. So there are many subtleties, and there were some papers claiming something wrong, and here we could check, okay. So it shows, this is the justification of the title of my talk, you know, high precision in the comparison between PN and PM, and everything works. At the end, everybody is very happy because the very complicated Calabi-Yau type computation of Plewka agrees with the complicated Tutti Frutti computations, okay? That's the point I want to say. And numbers we had computed like this, at 7.5 PN level, actually it's 6.5 PN level, agree nicely with the, but we could get the next order in U also from this anyway. Just to give you a flavor that there is a comparison. Now I will not spend time of the comparison. Before I said that you use numerical relativity by comparing a waveform computed during the merger of two black holes and a numerical relativity computation of the waveform. But you can do something else, which is you can do numerical relativity simulation of scattering. You put on the computer two black holes going like this, and you compute the scattering on the computer. Actually, we were the first one to do that in 2014 with Rezzolla at AEI at the time. And recently, we have used new platforms to compute this. And let me just show that if you use the effective one-body representation of the potential between two bodies, you can compare at 4 p.m. the numerical relativity values of the angular scattering angle chi, which are these dots here, these crosses, and the EUB resum radiation reacted 4 p.m. So you see there is a beautiful agreement at 4 p.m. between numerical relativity computation of the scattering angle and analytical description, okay? And if you are not at 4 p.m. but at lower p.m., this is less good. And also, if you use the perturbative expansion of the scattering angle, saying the scattering angle is 1 over j plus 1 over j squared, you get a very bad agreement. You get something which is here, which is a factor 2 too small. So it's just propaganda to see that EUB is, and it works better than other things. And beautiful things, using something hidden in Landau-Lifshitz, which is called, in an exercise of Landau-Lifshitz, the Firsoff inverting, okay, the Firsoff formula says that if you know the scattering angle for a fixed energy, but a function of a varying impact parameter, So you know the scattering for continuous value of the impact parameter. You can reconstruct what is the potential, V, that gave this scattering angle. And we could do this numerically. We could determine from numerical relativity the EOB potential and then compare to the best 4 p.m. EOB potential, okay? And there is a difference, not small, I mean small, but not zero. So it is the beginning now of a different way of using numerical relativity to learn something about the interaction of two black holes. It's just a different synergy. Just, maybe I will not spend, let me just say without spending time, in recent work that I'm doing with Ulrich Speraker and a very gifted young Indian researcher, Tamana Jain, we are computing now the scattering of boson stars, solitonic boson stars, which are extremely compact, you know, objects made of field energy, okay, with this type of Lagrangian, with this potential for the scalar field, complex scalar field. These are stable objects, and then instead of having two black holes scattering, you can make two of these objects scatter, and then you can compute the scattering angle and compare to analytical results, except that the analytical results do not exist in the literature. So we had to compute, this is simple, it is the one, I mean, we had to compute gravity things and scalar exchange, and these have not yet fully computed, so it's a new challenge of doing computation with scalar field exchange. And at the end, there is a beautiful agreement between numerical relativity points, which are the dots, and analytical description of them. Okay. Now, in the last, yeah, we started late because we were waiting for you, no, Massimo? So I have still a few minutes. But you are, if you want to, if you have other things to do, you can leave, okay? I won't be vexed. So, about the waveform, okay. Post-Minkowskian gravity and quantum computation can not only compute the scattering amplitude of two black holes going into two black holes, a 2-to-2 amplitude, a 4-point amplitude, but they can also compute a 2-to-3 thing, which is you have two incoming particles, massive particles, and in the out channel you have the same massive particles and a graviton. So you compute the emission of one graviton from the scattering of two bodies, Bremsstrahlung computation. Okay? In the past, the only result which existed was an old result of Kovacs and Thorne, which was at the level which now one calls tree level. Tree level would be this diagram if you add nothing else. Okay, you have just one graviton exchange and nonlinear effects. And recently, they could compute one loop emission. One loop means you compute these diagrams where you have two massive particles coming, two going, and a graviton emitter. But then, from this computation, from the T matrix, you need to compute the waveform, and there are subtleties. Before describing the subtleties, because you know the main theme of my talk here is to say that over the last years there have been useful synergies by comparing methods like post-Newtonian, classical computation, and this modern computation, and numerical relativity. There are many ways of comparing this to this, and this way we learn things. Everybody is learning new things, and we understand better the physics. Now, the way to all the waveforms which are used by LIGO, analytical waveforms, are using the formalism we introduced long ago, called the multipolar post-Minkowskian method. This method solves Einstein's equation. I will not describe. It solves Einstein's equations in a post-Minkowskian way with multiple expansions, and then it matches to a system of two bodies in the middle by using post-Newtonian information. So it combines various types of things, and at the end, you can compute explicit waveforms from this. And they are the ones used, actually, really, in all computation at higher level by LIGO type things. At the end, this method gives that the waveform at infinity, including tail effects and tail of tail, etc., and many nonlinear effects, is an expansion describing the waveform in terms of radiative multiple moments at infinity, but relating the waveform at infinity to the quadrupole moment of the system, the octuple moment of the system, via nonlinear effects, via non-local in-time effects. I do not write the full formulas, there are complicated formulas that were derived. And recently, what we did with Donato, Bini, and Andrea Girardico was to compare what we had computed by the multipolar post-Minkowskian to the latest quantum computation of graviton emission, okay? And this led to some surprises. So the final result is fully explained in this paper, a tale of two formalisms with, so it's a collaboration between people from the classical GR point of view and people from the quantum amplitude community, particularly Stefano De Angelis, Radu Roiban. And I will not describe everything, but just subtleties here. Because at the beginning, 3 different groups computed the one loop waveform, and then we compared their result to our result. And then there were discrepancies even at the Newtonian level. So we asked them, are you sure of your result? Because it's not even correct at the Newtonian level. Then people understood, Simon Caron-Huot said, but you must take into account in the K-Mock formalism extra cut terms that are very important, okay? And then there were more subtleties. I will just say, what is the subtleties linked to infrared effects? And in particular, the final amplitude, what is computed is the connected amplitude. Connected amplitude means you always have things connecting the gravitons, connecting the world lines and the emitted graviton. But you must add by hand disconnected amplitudes. For instance, this diagram is not computed because it is too trivial and it corresponds to a constant background. This diagram means you have two world lines going straight and they create a Coulomb field, GM over R Schwarzschild linearized field, okay? And it is at 0 frequency, okay? So the point is that these are 0 frequency gravitons that are not included in the quantum computation. But because they are cut terms. Cut terms means there are extra contributions that mix subdiagrams, and this cut term includes these 0 frequency gravitons. So you must add the 0 frequency gravitons even if you are interested in non-zero frequency terms, just to show you, because some of these terms were not included initially, and that created a discrepancy. And then the final amplitude is infrared divergence. That's why I was showing this. But there are two types of divergences which are of separate physical meaning. This G over epsilon is linked to the Coulomb logarithmic phase at infinity, while this extra term is linked to the fact that that Simon Caron-Huot pointed out, that should be there also, is linked to the fact that the two incoming world lines, because they interact by Gm over R Newtonian force, they have a logarithmic drift. Okay. World lines do not have a limit in space-time. They have a logarithm thing, because the 1 over R square force, when you integrate it, give a 1 over R delta P and a log of R delta Z. Okay? So, and this gives another log and another infrared. So anyway, at the end, taking into account all these effects, we reach perfect agreement between the MPM formalism and the quantum amplitude, and both communities learn things, okay? So it's just this comment I wanted to make. Final is the final thing, essentially. Then I have the conclusion. Just to say that they are puzzles, because up to now I said, yes, we compare this, and it works beautifully, okay? There are things we do not understand. We do not understand high energy behavior. The computation of the loss of energy by the Bremsstrahlung is such that if you have a sufficiently high Lorentz factor, you lose more energy to gravitational waves than the energy of the system. So definitely there must be a limit to this formula, and we don't understand how it happens, okay, yet. And there is a discrepancy between effective field theory and other computation, tutti frutti, at 5 p.m., which have been only partially understood by the group of Porto, Riva, Young, 24, but not fully understood. So, but this is nice. I mean, it's nice to have puzzles because it means there are things we still want to learn, and we will learn. So the conclusions is just, in this diagram, I have illustrated the synergies, you know. EOB, which is an analytical thing, can enter in dialogue with numerical relativity, with post-Minkowskian, with post-Newtonian, with everything, with scattering amplitudes, and can take information from these and then give back this information to make better waveform, hopefully for LIGO. Okay. Thank you for your attention. Yes?
So you explain how you can use numerical relativity to find coefficients that go into these analytic methods. Can you use the analytic methods to speed up numerical relativity? For example, you could imagine, instead of computing everything for two black holes in numerical relativity, saying, I already know that the orbit is more or less the effective one body.
Exactly. And this is done. This is done, and it allows not to compute very long waveforms. Actually, I should say that there are two ways to do that. The EOB way is you use EOB all the way, and you take some information from NR, and then you can start the waveform at some point. Other people try to use to make hybrid waveforms, saying we will combine a numerical relativity waveform after some time with analytical post-Newtonian waveform before this. Okay. The problem is that in general you need to start maybe too early and things like that. I should say also that there are now purely NR surrogates, that is to say, if you have sufficiently many numerical relativity waveforms, you can interpolate them, but they are always quite short. If you want a waveform which lasts, you know, for several minutes, you need analytical thing, because the longest waveforms do not reach more than 1,000 cycles or something like that.
What I meant something a little bit different. I'm saying, like, imagine a numerical relativity simulation, but built in the simulation, I'm saying that I know that EOB is pretty close to the real solution, and so I use the NR to compute deviations away from EOB.
That's a good point. The problem is that what makes EOB efficient is to work only with gauge invariant things like phase, scattering angle, why when you do a numerical relativity, you need to know the full metric in space-time, and it is not an information that EOB can provide completely, okay? So it will be difficult. And then finally, numerical relativity needs to start at some moment and compute the full space-time anyway. But people are thinking. Too much information.
It was a good overview of the bird's eye view on this subject. Impressive. So, I imagine that you and all the other group are in constant contact. And
yes.
So, what's the role of, say, LIGO or Virgo? They are just users that on which you feed the results,
yes.
Or they come with demands and say we want them.
No, they are essentially users, okay, and although some people from the like Vibern, for instance, now when they give talks, they say we compute this because it's directly useful for LIGO, which is not true, because actually what they do is not useful by itself. It has no connection with LIGO. You need to inject it, the information, somewhere else in a formalism, which maybe UB or another one, because there are other ones, and then you have something useful for LIGO.
But if you are not doing it for LIGO, why are you doing it? This is my main question. You are certainly, this is a strange way to improve predictions for LIGO, right? It's not the most straightforward way to improve predictions for LIGO, doing scattering
yes.
Of unbound orbits, right? Clearly you are doing it just for the fun of it. But where is the fun?
No, the fun is, okay, first, Is it recorded?
No.
because, because, okay, Zwibern could not go beyond 5 loops, okay? And
that's fine.
He had technology.
I will show the bastards. That's the fun.
He had technology to do that. Very beautiful, using double copy. The fact that Einstein is the square of Young-Mills is a fantastic thing, which comes from string theory. This came from the vertex operators of string theory, that you see this, and it is practically useful. So he was very happy when I said, I urge amplitude expert to do that, to say, here I come, and then I compute something that will be useful in some way. I mean, people are doing what they can do, and at the end, this is useful. All this dialogue and synergy, at the end, will be useful, because
Also, I thought that you use this scattering data to then reconstruct the potential.
yes, we reconstruct the potential, and then you use it for the merger. I should say that there is one claim. Okay, for the moment, LIGO has observed 300 merger events, and there is a claim that one of these events might be a capture event, which means scattering and then
Really?
becoming bound.
Oh. So,
And
but
you
not
expect-
merging, but not merging.
No merging.
Oh, okay. so-
Not yet. Not
but
yet.
starting
Maybe
from,
maybe there is
Merging
even
from a
claim.
hyperbolic
starting
orbit.
from a-
But maybe
hyperbolic,
there
yes.
is even a claim, some of these things are strange and could be interpreted as a Bremsstrahlung waveform, just passing and creating
and no
waves.
merging.
And no merger.
Interesting.
We don't know. What is sure is that soon LIGO will have thousands of signals, and some of them will come from very dense environments where you could have Bremsstrahlung and things like that. So in the future, there will be events,
Yeah.
Bremsstrahlung events. But for the moment, among the 300, I think 299 are merger events. Okay.
And do we expect that we'll see individual Bremsstrahlung or more like a background?
The future will tell.
Okay. But there's no way to estimate, like.
I'm not expert on this. I guess some people have.
Because Bremsstrahlung you can only get like in a globular cluster.
Yes, in globular
because-
cluster. But you know, something surprising also from the LIGO point of view, they observe merger with black holes of 60 solar masses and 40 or whatever. Something that people say that are impossible to make from stars.
Still now? I thought they revised the statement.
I think that the idea is that these very high mass black holes
Our second generation.
are second. They were made from mergers of
Yeah.
the past, because we see 30-30 giving 60.
Okay.
We don't know. So anyway, it's true. There is a zoology of new things that people are explaining, and some of them we don't know if those binary black holes they are in the field or they are in the globular cluster. Do they need a dense environment? Can they be? There should be differences. The spin, there is 1 or 2 events with very high spins also. Most events have low spins. And then you think maybe they come from slow things. But if they are high spin, you think maybe in a globular cluster, you know, you capture something which was sped up before, spun up before.
Or some of them have confirmed high spins
Yes,
of the
there is
emerging
one.
objects.
Yes, recently there is a confirmation for 2 objects higher than 50% of the limit, Kerr limit. I mean. So it's known. Most of them are below 10-15% low spin, but there is proof, and also apparently precessing. So things where the spin are not, you know, because you could have low spin and align with the angular momentum of the system. But now there are systems where the spins are doing this.
And those you are saying could only be recently formed or something.
Or they were in a global. Okay, I'm not expert at all on the astrophysics, but it's clear that now there are new type of data. And
No, but
among
you surely are an expert in this thing. Suppose I
No.
start with eccentric orbit with misaligned spins. If I allow them to gradually merge, I know that they do become more circular, right? This is a standard
circular, but the spins stay like
Oh,
this.
spins do not align?
They do not align. No. I
So
think.
the only reason for alignment of spins is some dirty astrophysics, not pure gravitational evolution.
Yes, I think so.
I see.
Like with a disk or something like this.
Like what? Sorry.
With an accretion disk or something like this. That's what you mean by dirty.
Yes, I should say, yeah. Most of these are.
No,
assumed to
I
be
mean
clean.
the reason for orbits to be circular is Landau and Lifshitz, right? Because if you start with an eccentric orbit, under the influence of gravity alone,
Yeah.
you become circular.
Yeah.
Because you
Oh,
lose
now
angular
Lifshitz.
momentum.
I think it's more
Peters.
Peters and
Huh?
Matthews.
Peters, yeah, Peters. They cite, I mean, the guy who
Or
did
they
this-
cite somebody who showed it.
Yeah,
Peters,
Peters, yes.
Oh, but
the
that's
60s.
trivial. You just compute radiation.
No, he computed angular momentum loss. It's
Right,
a
right.
non-trivial
But anyway.
computation he did.
But you are saying this does not
It
work
was in
for spins,
1970.
right? For spins it doesn't work.
Yes,
Right.
I think they are decoupled essentially, okay, and then they,
Until the very last
and
moment.
then I mean they spin orbit, they do this, but it does not align them.
In your formalism, where was spin? So you had
Most of what I've seen were no spins, okay. There is now recent comparison of spinning. Actually, one of the slides was about spinning scattering, but with aligned spin, which is not very difficult. They don't precise.
At what order do they come?
What's
In your formal expansion,
Ah, yes.
is it G5, G4, whatever?
So they have like what 2 or 3 orders of G immediately, okay? Because these are very compact objects, okay?
Right.
And the size of the thing determines the spin. So they indeed start at G cube compared to G or something like this, and then amplitude computation, or at least calculation by Plevka has allowed to compute spin effects in an efficient way. And now they are known to G5, that you say, taking into account the fact that the spin are small, at the level of G5, the only thing which is lacking is the non-spinning part, okay? All the rest is known.
But it looks like some sport or something, right?
In life, some people also Plevka jumped on this, and then
It's
also
more like weightlifting.
But I mean, why
you cannot do supergravity all your life, you know, or string theory. If there is something which is of direct interest.
Again, we need to improve precision on measurements.
Yes, I did not say that.
Way
In the
we-
future, you will need to improve numerical relativity and analytical relativity to have better and better waveforms.
If you think about G minus 2, now
Yes.
if you want to compare theory with experiment, you need to go to 4 loops plus, I mean,
Exactly.
excellent methods.
And
of
we have the
evaluating
same time of
the
thinking.
non-probability contributions.
I'm still surprised by your answer to my question about like using some analytical results to as a sort of background to numerical relativity. An example I would have in mind, imagine I want to compute a Newtonian trajectory around the sun, which has a quadruple moment, etc.
Mhm.
etc. I know that to lowest order is just going to be Keplerian, and then I have corrections. Why can't I just write a numerical code that only computes the corrections around that is fully numerical, but it uses the fact that I already have a really good approximate first answer, so that I
It
can
will
take
be
bigger
good.
time steps.
I still
you know.
think it's non-trivial because you need to evolve the full space-time. Okay, when you have two
Sure,
black
but-
holes, so it means
Yeah.
you need to have, and you need to evolve all those gauge degrees of freedom all over
But you
space
can't-
that do nothing, and to inject this
Yeah.
extra information. No, one should
From
think
from
more.
an EOB,
It's a good
from a
suggestion.
gauge invariant results, can't you just like make any gauge dependent thing that you want? It seems like harder to go the other way around, but like if you have a gauge
What
independent
is
thing-
true is from NR, you have essentially gauge thing that you do, but the waveform at infinity is gauge invariant.
It should.
So there, the difference between the waveform and the NR waveform in this, in principle, contains a lot of information there. Okay, but I still think you need to compute the thing. And also, I should say, at the beginning, we were hoping that a long waveform, we could extract, you know, our unknown coefficient D5 at 5 p.m. And the problem is when you have NR, you can check that it agrees with analytical thing, but when it starts disagreeing,
Yeah, is it
then
noise?
all the higher order terms become as important
Yes.
as this one, so it's very difficult to extract one coefficient at a fixed
Right.
perturbative order.
Mhm. Yeah.
Okay.
Thank you.
Good, so my computer is fine, I take it.